Yay, the last section from this unit. Okay, this one's going to be continuity. We've informally talked about continuity in the past as the idea of being able to draw it without lifting my pencil off the paper. And now we're going to analyze it a little bit more rigorously using the concept of limits that we've developed. Okay? So we'll say that a function is continuous at x equals a if the following three conditions are satisfied. Number one, you need the limit as x approaches a of f of x to exist. So I should say it doesn't exists. Limit as x approaches a of f of x exists. And remember, this in itself is three conditions, right? Because you have to equal something from the left, you have to equal something from the right, and you need those to be equal. And that's what makes a limit exist. So first condition is you need the limit to exist. The second condition is that you need f of a to be defined. So you actually have to have an output of the function. And then the final condition is that that limit there and then that functional value right there are equal. So let's just say it is they be equal. Okay, so three conditions. Limit exists, function value exists, they be equal. Okay, so looking at this table or at this graph right here, there are several discontinuity points. So what are the values of x where it is not continuous? So discontinuity at, we'll see where the x is, and then we'll see which ones or one of these conditions up here are violated by the picture. Okay, so the first discontinuity is occurring where we have to lift our pencil off the paper is that x equals -2. Okay, does the limit exist? Well, from the left, it's positive infinity, and from the right, it's negative infinity. So the limit doesn't exist. And furthermore, there is no closed dot at -2. Nothing on that vertical asymptote. So f of a is not even defined. So this one, x equals -2, violates both 1 and 2, and it has no prayer of doing 3 because it violated 1 and 2. The next discontinuity point, pencil lifts off the paper right here. That's x equals -1, and the limit from the left is -2, and the limit from the right is -4. So this violates condition 1. The limit doesn't even exist. Next, x equals 1, because I have to lift my pencil off the paper to continue over here. So this time the limit from the left is 1, the limit from the right is 1, so the limit actually exists. 1 is satisfied this time, but the function itself is not defined. There is no closed dot on x equals 1. So this violates condition number 2. And then finally, there's another discontinuity point here at 2. Here the limit from the left and the right are both equal to 4, so the limit exists. There is also a functional value, because when you actually plug in 2, you get the value of -1, so condition 2 is fine, but this one violates condition number 3, because in this case, those two things, the limit and the function value, are not the same. Okay, when we talk about these ones here, this discontinuity that flies off to infinity, we sometimes call this an infinite discontinuity or vertical asymptote. When we have a function that jumps between two finite values, we sometimes call this a jump discontinuity. And then when we have holes in our function, but the holes could theoretically be filled in to make me continuous, we call these removable. These discontinuities are removable. So those are the three major kinds of discontinuities. Infinite discontinuities or vertical asymptotes, jump discontinuities where you jump between two pieces of a function, and then removable discontinuities that hypothetically you could fill in the hole on. Okay. Let's rewrite this function without an absolute value. So remember that an absolute value function is going to be giving its output if it's positive, and it gives the opposite of the input when the input is negative. That's what absolute value does. So that denominator, notice, is x times x plus 3. So if I were to make a number line and put the values negative 3 and 0 on the number line, then over here we'd be positive, because you plug in infinity, or a big number, billion times billion plus 3. A number between here and here would be negative, and a number less than negative 3 would be positive. So the outputs of the x times the x plus 3 would be either positive, negative, or positive, depending on what intervals you are on. And so that means my f of x is going to be rewritten as a piecewise function with two conditions. One of the conditions is going to be the case if x is from negative infinity to negative 3, or from 0 to infinity, because that's going to be the positive place. And then there's going to be a second condition if x happens to be between negative 3 and 0. If you are positive, then your output is just x times x plus 3. It's just whatever that thing is, because this value is positive. So here you would get x plus 3 over x times x plus 3, which is actually just known as 1 over x if we wish to simplify it. So the output would be 1 over x if x were in this interval. And down here you'd be getting x plus 3. But since you are negative, you'd get the opposite of that thing in the absolute value, which would be a negative x times x plus 3. And so this output is going to be negative 1 over x if you happen to be in between negative 3 and 0. Notice both negative 3 and 0 themselves are undefined points. Okay, so now to graph this function, x equals 0 is a vertical asymptote. So I will draw in my vertical asymptote at x equals 0. For the values that are above 0, the function is 1 over x. 1 over x is the inverse variation graph, right? The reciprocal graph. Furthermore, if you happen to be in the interval from negative infinity to negative 3, you also equal 1 over x. So it would be on this part, but only from negative 3 on. So if I plug negative 3 in, I get negative 1/3. And then there's the part over here. Okay, what happens between negative 3 and 0 is that instead of being the 1 over x function, it's the negative 1 over x function. So it's the flip over the x-axis. If I were to replace x with negative 3, negative 1 over negative 3 is positive 1/3. And it would be the negative 1 over x graph, so it would look like this. And so what I've successfully graphed now is I have graphed the function. First of all, I wrote it as a piecewise defined function without the absolute value. Then I graphed it. And notice that the function is not continuous. Not continuous at x equals negative 3, where you have a jump discontinuity, and not at x equals 0, where you have an infinite discontinuity. So now, based on space, I won't put the justification here, but this is a jump discontinuity because the limit from the left is negative 3, the limit from the right is positive 1 over 3, and therefore the limit doesn't exist, which means that you are discontinuous. Here, I guess you could say the limit as you approach from the left or the right towards 0 is positive infinity, so there's a way you could say that this exists, but the functional value is not defined, so it's definitely a discontinuity there as well. So, how about this problem? Sketch the graph, label everything, do all the stuff that we know how to do from pre-calc, right? So that function is x plus 2 over x plus 1 times x minus 1. And this function is x plus 4 times x plus 3 over x plus 3 times x minus 1, which would be almost equivalent to x plus 4 over x minus 1 with a whole, right, with a whole at negative 3. Okay, for the values bigger than or equal to 0, I'm going to graph this function. This function has vertical asymptotes at negative 1 and 1, but I only care bigger than or equal to 0. So I only care about the asymptote I'm getting here at x equals 1. Then, let's see what's happening over here. The horizontal asymptote, since it's linear over quadratic, is going to be 0. So I have a tendency for it to go towards 0. And then let's see if it's above or below. It's going to equal 0. Where's its x-intercept? The x-intercept would occur at negative 2. And then that means that there are no x-intercepts over here. So am I above or am I below? Let's do that by sticking in 2. 2 plus 2 is 4. 2 plus 1 is 3. 2 minus 1 is 1. That's going to be positive. So my sketch of my graph is going to look something like this. And then I continue to have graph bigger than or equal to 0. So I also need to see what happens when I plug in 0, which is 2 over negative 1. That's a negative 2. And then that's going to be the part over here. So this is the graph of the x plus 2 over x squared minus 1. On the other side, I will graph the x plus 4, x plus 3 over the x plus 3 times the x minus 1. I should have rewritten this down here when I was doing everything else, I think. But okay, at any rate, we're going to have a whole at negative 3, and negative 3 is less than 0. Remember, this is on the domain x less than 0. We have a vertical asymptote at 1, but that's not part of our domain because we're only looking less than 0. And we also have a horizontal asymptote at at y equals 1 because the top is linear over linear. This says that we have an x-intercept occurring at negative 4. 1, 2, 3, 4. The y-intercept would be at 0 plus 4 over 0 negative 1, 0 minus 1, so that'd be a negative 4. So our graph would look something like this and that. But then there is also going to be a hole at negative 3. And then that's our graph. Okay, let's label all of our useful information. So there's a 0, an x-intercept located there at negative 4 comma 0. There's a hole located at negative 3 comma negative 3 plus 4 is 1, and negative 3 minus 1 is negative 4. So that'd be at negative 3 comma negative a quarter. We have a y-intercept located at 0, negative 2. Let's put this is not a y-intercept here, but I still got to label it because it's useful information to see, I think. This is a intercept at 0, comma negative 2. And then don't forget this one also had its horizontal asymptote there. Okay, so I'll go back and look at the questions now. So A is sketch the graph, label intercepts, asymptotes, discontinuities. Looking pretty good. B, identify discontinuities as removable, finite, or infinite, justify with limit statements. Okay, so the discontinuities are occurring at x equals negative 3 is removable because the limit as x approaches negative 3 of our function f of x is equal to negative 1/4. So this is a removable discontinuity because it could be filled in. And it has a limit. There's a discontinuity at 0. X equals 0 is a jump, right? From the left and the right, it equals different things, and it's a jump because the limit as x approaches 0 from the left is going to be negative 4 equals negative 4, and the limit as x approaches 0 from the right is equal to negative 2. And then we also have a discontinuity at x equals 1, and that's our last one. X equals 1 is infinite because the limit as x approaches 1 from the left of f of x is negative infinity, and the limit as x approaches 1 from the right of f of x is equal to positive infinity. So that would be the limits, or sorry, the discontinuities with the type and the justification. And then the last part of the problem was to find all the equations of the asymptotes. So there is a vertical asymptote, here is a horizontal asymptote, and here is another horizontal asymptote. These are the justifications for the vertical asymptote, and then the justifications for the horizontal asymptotes would come from the limit of f of x as x goes towards infinity, which would be meaning that we're following this function, right? This function as x goes towards infinity would be linear over quadratic. That's 0. And our justification over here is the limit as x approaches negative infinity of f of x equals 1, and that's from this horizontal asymptote being linear over linear, providing the 1. Okay, so that's one beefy problem, but a lot of this was already done in our previous unit, and now we're just putting our limit language on top of it to make it more formal. Okay, let's see. These ones will hopefully go a little bit faster. Is this function continuous everywhere? Well, there's only one issue, right? 1. All of the other numbers are fine. Any number you plug in here except for 1 is good, and you even have a value when you plug in 1. Namely, you get 3. So let's first check to see if we have a limit. What is the limit? As x approaches 1 from the left of g of x. So that means we would be coming in on this part from the left, which would be 3 over 0. That's either plus or minus infinity. Which is it going to be? Let's see, if I plug in a number that's a little less than 1, the top will be 3, and the bottom will be 0.9 minus 1, which is negative, and a positive over negative is negative. So this answer is going to be negative infinity. And then the limit as x approaches 1 from the right of g of x is also going to be plus or minus infinity. It's also going to be this 3 over 0. But this time we would be getting a plus over a plus, so we're going to be positive infinity. So our limit doesn't exist. So no, not at x equals 1. We have no limit. It's an infinite discontinuity. It's a discontinuity, and we can tell what type it is because we are going towards infinity. Okay, problem 5. Find a value that will make this be continuous at x equals 1. So we want to force it to be continuous. We need that limit to exist. So what is the limit as x approaches 1 from the left of f of x? Well, that'll be the limit as x approaches 1 from the left, means we're on this part. And if we were to replace x with 1, we get 1 squared, which is equal to 1. If we approach 1 from the right, that means we're on the other branch. We're on this branch. So we'd have the limit as x approaches 1 from the right, sine kx. And that's just replace x with 1, and we just get sine of k. So we can make the limit exist as long as we make sine of k be equal to 1. which means, let's set those equal to 1. That would mean that k would be equal to, let's see, where sine equal to 1, pi over 2 plus 2 pi k for k an integer. Oh shoot, I have k in two places now. Okay, we need k to be equal to pi over 2 plus 2 pi l for l an integer. What an inconvenient choice of variables. But at any rate, this will force the output to be 1, and we did this by making the limit exist, and this makes sure that the functional value exists, and by setting them equal, we have made sure that they're equal to each other. So we have justified the continuity. Okay, next, last page. Find the values of the constant k and m, if possible, that will make this function be continuous everywhere. So here there's two issues, right? There's an issue at -1 and there's an issue at 2. So let's set them all up. What's the limit? As x approaches -1 from the left, means we would be following this rule. Plug in -1 would give you -2 minus 1 is -3 plus 7 is 4. Limit as x approaches -1 from the right of f. We're now on this interval, so we'll follow this rule. Replace x with -1. -1 plus 1 is 0. 0 times m is 0. So we just get a k. So k equals 4. We need to make these two be equal so that way we get our continuity at -1. And now let's do the continuity at 2. The limit as x approaches 2 from the left of f, so we're a little bit less than 2, means we're in here. 2 plus 1 is 3. 3m plus k, but I already got what k is. K's got to be 4, so I'm using the k here. Then we need the limit as x approaches 2 from the right of f, which means we're on this rule. And if we were to plug in 2 for x, we'd get 2 squared is 4, 4 plus 5 is 9. So here we would need 3m plus 4 to be equal to 9, 3m to be equal to 5, and m to be equal to 5/3. So that helps us to be continuous at all points for this function. Okay, last concept, a reminder, seen this in Algebra 2, the intermediate value theorem. What the intermediate value theorem says is that if f is continuous on some interval a to v, then f will take on every value between the minimum and maximum value of f on the interval. Okay, so what does this mean in picture form? It means that if we have some kind of crazy function, I'm drawing it increasing just for ease right here, but it really doesn't matter. And if it's on an interval and there's an a and there's a b, that means that this is f of a and this is f of b. And what this theorem is saying is that if you give me absolutely any value between that high value and this low value, it's called y star, then there must be some number between a and b, call it c, where when you plug c into the function, you get that y star. And that's true for any value between the smallest value and the largest value you ever take on. Okay, so where can this be useful for us? Well, let's use that to show that this function, that this equation must have at least one solution. So the way I'll do this is we'll set it up as a function. We'll say let f of x equal x cubed plus x squared minus 2x minus 1, which is a polynomial, so it is continuous. So now we have a continuous function. Notice, what is f of 1? 1 cubed is 1, 1 squared is 1, 1 plus 1 is 2, and 2 minus 2 is 0, minus 1. So f of 1 is negative 1. And what is f of 2? 2 cubed is 8, plus 4 is 12, minus 4 brings us back down to 8, and minus 1 is 7. So f of 1 is negative 1, and f of 2 is 7. So now, by the intermediate value theorem, since negative 1 is less than 0 and 7 is larger than 0, there is a c located somewhere between 1 and 2 with f of c, which notice is c cubed plus c squared minus 2c minus 1, equal to 0. In fact, there's a place where it has to equal negative 1/2, there's a place where it has to equal 5, there's a place where it has to equal 2, but there's definitely going to be a place somewhere between 1 and 2 where we equal an output of 0. And so, if we add 1 to both sides, c cubed plus c squared minus 2c equals 1 here. And that completes a proof. That's how we use the intermediate value theorem to show a certain point exists without even having to find it.